In this video, we are going to discuss the inverse function theorem, which gives us a way to try to ascertain whether or not a function can be inverted, or more specifically, what's called locally inverted. To understand that terminology and how the inverse function theorem will work in general, let's look at these four pictures. So here we just have four functions, which are scalar value functions of one variable. We can graph them in R2. They all have the form y equals f of x. If you look at, say, these three, so the top left and the bottom row, just based on the way I sketched these functions, I would say that all three of these functions appear to be globally invertible, meaning that we can flip them over the line y equals x. That's how we invert graphs in R2. We could say that, it's not just the case that given an x value, there's a unique y value. For each of them, given a y value, there's a unique corresponding x value. In other words, each of these functions here and here passes what you could describe as the horizontal line test. Okay, the question though is what if we're not looking at the function? How could we try to figure out, just based on, say, data or information about the function, if we can perhaps do this kind of inversion? So here, this function, looking at it, it's a nice monotone increasing function. How do you detect that a function is increasing or decreasing using calculus tools? You look at the first derivative. So here, if I look at, say, this particular point on the graph of this function and I took the derivative, I would get a positive number. And that would tell me, it's probably the case that around this point, our function is strictly increasing. And therefore, if I just kind of zoom in right here, we pass a sort of horizontal line test, and therefore this function is locally invertible. Okay, this is kind of the nicest function here. Let's look now at this function on the top right. I've highlighted 2 points here. Probably the first thing I should mention is that this function is not globally invertible. It does not pass the horizontal line test at all because we have this place where if you draw a horizontal line, you would cross the function 3 times. However, if I look at, say, just this point right here, and I say, forget about the rest of the function. Let me just kind of zoom in around this point. If I'm just looking around this point in some neighborhood of this point, there, my function does pass like a local horizontal line test. And just here, if I throw away the rest of the function is invertible. So this is a locally invertible place on the graph of this function. Again, how would you figure that out using tools? Well, you could say right here, our derivative is again positive like it was over here. So our function is increasing in some neighborhood around this point. So if I'm just looking in the neighborhood around this point, I can invert there. On the other hand, I've also highlighted a point where we clearly cannot invert. So if I try to draw any kind of neighborhood around this point and imagine a horizontal line through it like that, we are going to intersect the function twice. So around this point, I am not at all invertible. Okay, so to recap, based on these two pictures, here and here, I had a nice positive derivative, and I said that means, if I look just around these points, we have a strictly increasing function, so we can invert. Here we had a derivative which is actually 0, and I cannot invert. However, here, my intention with this function is that it looks kind of like y equals x cubed. Here I have a 0 derivative, and yet I can invert, assuming I'm just kind of turning flat instantaneously right here, like on y equals x cubed. And here, this function is strictly increasing. It just so happens that right at this point, I cannot take a derivative. So the test I used here and here doesn't work here. Okay, so to summarize, when we look at functions of one variable, we are looking for something like strictly increasing or decreasing behavior. That will allow us to know that we can at least locally invert, like we do here. However, the check for increasing or decreasing behavior amounts to taking the first derivative, and that's not always going to be conclusive. Here we had a first derivative which was 0, and it's just we can't really conclude based on that. It could be not invertible locally, or it actually could be invertible locally. So having a 0 derivative was not conclusive. And here it just so happened that the function wasn't even differentiable. Okay, at the risk of spending too much time on these 4 examples, I want to say that the inverse function theorem is like these 2 examples. So it will work sometimes to allow us to say that locally, like here, we can invert. Let's now look at the general statement for a function which is a map from, say, Rn to Rn. So we want to take our knowledge of functions from R to R and kind of grow it into a larger statement. The inverse function theorem is a tool to help us try to detect when a function is locally invertible. It does not always apply, but when it does, here's how it works. The hypotheses on the left, I've broken it up into three, but the first two are really just saying we're working at a point in a nice domain for a function. So imagine we have some open domain A in Rn. Again, we're scaling up from functions from R to R to functions from Rn to Rn. So on some open subset of Rn where we are going to detect invertibility around some point, like those points I highlighted a moment ago. Imagine the function we're interested in inverting is at least C1. So at least continuously differentiable, if not more. Okay, so then here's the real test. Compute the Jacobian matrix for f at P, and then compute its determinant. So that's just a number. If that determinant is non-zero, then the inverse function theorem applies. So this last part is really like the test. And having a determinant which is not zero for the n by n Jacobian matrix that we would compute for this function is like saying that the Jacobian matrix is invertible. Going back to the case for functions from R to R, if you have f prime at P, this is just a number for a scalar valued function of one variable. Numbers are invertible when they're not zero. You can do that. That's the inversion, right? So here we're saying, can I invert the Jacobian matrix? And if you can, so if the determinant's non-zero, telling us that the Jacobian matrix is invertible, the conclusions apply. Let's talk about these in just a moment. Before we do that, though, let me just say that what the inverse function theorem is telling us is that if we have a nice enough function, and then we look at the linear transformation that we associate to that function at P. So again, think of this matrix as associated to the action of a linear transformation, giving us that first order approximation for f. If we know that that associated transformation is invertible, then that behavior carries back to the function. So it's like this information about the transformation that approximates our function or gives us approximate behavior, being able to invert the associated linear transformation carries back to the original function. However, if you have a linear transformation defined by some matrix, if you can invert it, it's a global inversion. You're just inverting a matrix. But knowing the behavior right around P does not extend to a global ability to invert F. And so keep in mind here, we're just talking about local inversion. In some neighborhood around P, F is really well approximated by its first order linear approximation. But away from P, we can't extrapolate any information from this computation. Okay, take a moment just to think about that, then read the conclusions. I'll come back and talk through these. I'll say that this first piece here, which is like really the heart of the local inversion, this will make more sense when we actually look at an example and I sketch the neighborhoods U and V. So if this doesn't resonate with you quite yet, just stick with me until our first few examples. Okay, so thinking about these conclusions here, the first one is really the heart of the argument that F is locally invertible. We are not going to prove this. So that speech I just made about F is really well approximated by an invertible transformation and that property carries back to F, that's just a plausibility argument that just gives you a feel for why this theorem works, but it's not a proof. I might upload a video proving the inverse function theorem, but it's a pretty technical proof and it would take up way too much time in this video. So I'm going to just say that our understanding of the Jacobian matrix carries back to F, and that's as much as we will say to justify this first statement, saying that F can be locally inverted. It gives us the existence of neighborhoods U and V, but at the moment you might not know like how would you picture that, so I will show you in an example. The second conclusion is that the inverse function, so this inverse mapping from original outputs back to original inputs around the point in question, has the same level of smoothness as the original function. And therefore, it's at least differentiable. And actually, we have an explicit way of computing its Jacobian matrix right around the point in question, so in this local neighborhood area. This part is actually quite quick to compute, so we will prove this third statement. That just amounts to using the chain rule. I should say before we move on that the inverse function theorem gives us existence, but it doesn't tell us how to compute the inverse function, and in many cases you can't. So here we're saying that we know that F is locally invertible, but it doesn't give us a constructive way to actually get what the inverse function is or these neighborhoods even. So, I mean, you can do some thinking about the neighborhoods, but basically it's a theorem that tells you that an idea is possible, but not that you can explicitly do it. While the inverse function is mysterious and you may not be able to compute it, around the anchor point in question, so in the neighborhoods that we define, you can explicitly compute the associated Jacobian matrix for the inverse function. So I think that's very neat. Let me quickly justify this formula. I'll show you where it comes from. The first thing I should probably do is justify that this matrix inverse on the right even exists. So how do I know I can invert the original matrix around the point P? To do that, you want to think about the determinant function. So when you compute the determinant of an n by n matrix, you can think of that as a function on n squared inputs. What does the determinant do in coordinates? It multiplies things together, it subtracts things. Even if you just look at a 2 by 2 matrix, you can see it's this times this minus that times that. That's the action of a polynomial way of combining the coordinates. So as a function, the determinant is a map from Rn squared to R, which is continuous. Therefore, if df at P is invertible, let me rephrase this in terms of the determinant. If the determinant of the first Jacobian matrix that we compute, so this is our test, if this is non-zero, then the neighborhood U that we build up around P, where we want to say our function is locally invertible, we can design that neighborhood to insist that the determinant stays non-zero. I'm not going to say too much about like how to design U here because that goes into the proof of the entire statement. But basically, when we make that neighborhood U, we will make it in such a way that we insist that this continuous function be non-zero. Det of df of x is non-zero for all x in U. Just quick sketch of why that's true. This is a very quick argument to make about continuous functions. But if we have a continuous function, which is say positive up here, here's 0, because it's continuous, this isn't a jump discontinuity. You can make a neighborhood around this point where if the function is positive up here, it's positive in the entire neighborhood. So we can't just suddenly jump up to a positive number with a continuous function. That's just an epsilon delta argument about continuous functions. So let's move on now to using the chain rule to get this actual formula. Okay, so we can compute the right-hand side, and let's show where it comes from. Notice for any x and u, if I do the inverse function composed with the original function evaluated at x, this is just the identity map. Each of these functions is at least C1. The composition is at least C1. So we can differentiate using the chain rule on the left-hand side. We'll have the Jacobian of the outer function evaluated on the inside times the Jacobian of the inside function. That's going to give us df at x. So this product is our chain rule applied to the left-hand side of this equality. On the right, the Jacobian for the identity map is the identity matrix. So differentiate both sides of this. With the chain rule, you get this left-hand side. On the right, it's just the identity transformation. And now because we've designed U so that this matrix is invertible for all x and u, we can actually invert and say that while I do not necessarily know what this inverse function is, there may be no way to find it, I can give you its best approximation. I just think that's really neat. So I can know what its associated Jacobian matrix looks like, and it would be the inverse of this. It's an easy thing to remember. The transformation of an inverse is the inverse of the original transformation. Forgot to invert. There we go. Okay, so the Jacobian of the inverse is the inverse of the original Jacobian. It's just a really nice symmetry, and it makes sense once you apply the chain rule to our original composition. And I like to use this fact. Since we often cannot actually invert the function, sometimes when you look at examples with the inverse function theorem, it's just a question of saying like, yes, it applies. And it feels like you can't take it any further. But in our example, let's say our next example, what we will do is actually try to bring this into our analysis so that we do something useful with it. The inverse function theorem is a statement about functions from Rn to Rn, which means that if you want to give a picture of what's going on, you're really reducing down to the case from R to R. So that's the only one that you can really sketch in full detail. So consider this example. It's kind of like our warm-up examples, but this time we know explicitly what the function is. So f of x is x cubed over 3 minus 2x minus 1. We can look at this and say that around this point, which is the point 3, 2, the function is locally invertible. It's certainly not globally invertible. As you see, it doesn't pass the horizontal line test in general. But if I just zoom in here, I see what looks like a strictly increasing function. So our function is locally invertible. Let's take the fact that we totally understand this function just from looking at the picture of it and map all of our understanding onto the inverse function theorem. So if you think back, I gave the hypotheses as 3 conditions, but the first 2 were really just saying make sure you're working in a nice domain with a nice function. Here, this function f is a map from R to R. 3 is like the point P. A is the entire real line. Okay, so let me write this down. So f is a map from the entire real line. That's a nice open set back to the real line. 3 is the point in question. This function is totally smooth. It's a polynomial, so we can definitely say it's at least C1. It's smooth. So then the third condition is what you really are testing here. I'm going to write df at 3. That's what we would normally call f prime at 3. This is a 1-by-1 matrix. So it's just the scalar f prime at 3. And let's see, what is that? 3 squared is 9 minus 2 is 7. The determinant of that is non-zero. Again, this is sort of a strange way to analyze a function of one variable, but I just want to match the language and terminology that we had in the statement of the theorem. That's it. So we've now tested the inverse function theorem and it applies. So this check right here, that our little 1-by-1 matrix is invertible, which for a 1-by-1 matrix, we just know it's not 0. That tells us that the inverse function theorem applies. So looking around this point, our function is indeed locally invertible, as we were already able to see just from the picture. Okay, so thinking about the conclusions now, it said that there was a neighborhood U of 3 and a neighborhood V of f of 3, which we know to be 2, so that if you just look from U to V, the original function f is a bijection. Here are neighborhoods that would work. They are not unique here, so I've picked a U around 3 and a V around 2, so that if we just look in this rectangular grid, f is a bijection. So ignore everything else. Just look at U cross V here. So this is like the Cartesian product U cross V. That's this rectangular shape. I hope you can see I've sketched around this point. So for every x value in U, so pick any x here, there is exactly one y in V and vice versa. So f maps U onto V in a way which is invertible. Okay, so we are 1-to-1 and onto just in this little rectangle. So while the theorem doesn't give you a prescriptive way to immediately say what U and V are, I wanted to give you an idea of what they look like and how, if you have more knowledge of your function, like I do in this case, I have the picture of it, you can imagine designing U and V. Okay, so I know that for this U and this V, my function is a bijection. The theorem doesn't tell me that these are the right U and V, though. It just tells me that it's theoretically possible to do this kind of construction. Okay, let's now compute the derivative of the inverse function at this point. We cannot invert this function. In fact, literally, we cannot because it's not an invertible function, but I cannot try to write down an f inverse here. However, what I can say is that if I look at f inverse prime, I'll just use the standard calculus notation, at f of 3, in other words, at 2. So 2 being the input for the inverse function going from y back to x. This is going to be the inverse of this. Okay, that's the idea. Again, weird symbols to use, but I wanted to make it look like the theorem. And of course, for a function of one variable, that is the same thing as 1/7. That's not hard to imagine in this picture. Let's see if I can add a tangent line here. Okay, if you have a tangent line, fairly close, this tangent line is slope 7. If we were to flip it over the line y equals x, it would flip into a line that has slope 1/7. So that's easy to do for this kind of function. Let's now take this information, the fact that we know how the inverse function behaves at f of 3, it takes the value 2. We also know what its first derivative is at f of 3, it's 1/7. We can now write down the first order approximation for the inverse function and use it. So that's what we're going to do. Let me step aside just for a moment so that I can erase this, and we'll come back and just answer that last part. I do not have the inverse function, so I cannot evaluate f inverse of 1.8, but I can approximate it. It's going to be equal to, or approximately, its first order linear approximation centered at 2, a point we understand, where I'm going to plug 1.8 into that approximation. So basically, it's approximately f inverse at 2 plus df inverse at 2 times 1.8 minus 2. So this is our first order approximation centered at 2, and then I've plugged 1.8 into that. F inverse at 2 we know is 3. This 1 by 1 matrix is 1/7, and then this is negative 0.2. So that's going to be 3 minus 1 over 35. I hope that's right. And that's our approximation. I can't tell you if it's exactly right, but what you could do is take this number, plug it back into your original f, and see if you get to approximately 1.8. If you did, you feel good about it. If you're way off, it means that probably something broke down. Okay, so this was using the theory that we've been building up to approximate a function which we cannot write down. If you want to change coordinates, for example, here we are imagining changing between rectangular and polar coordinates, you want to think that your coordinate transformation is somehow robust, that you can describe the same types of shapes using two different languages, the language of x and y versus the language of r and theta in this case. So, if you're translating between two different perspectives, you want to imagine that you can move back and forth, that you can say in rectangular, it looks like this, in polar, it looks like that. We need to be able to move between the coordinate systems. In other words, we want to think that at least locally, we can invert back and forth between them. So that's the idea of having somehow a good, non-degenerate way of transforming between two different coordinate descriptions. Typically, when we talk about polar coordinates, we just say x is r cosine theta, y is r sine theta. Here, I would like for you to have the perspective that x and y are outputs of a function from R2 to R2, where the coordinate functions where we're being sent to are r cosine theta, r sine theta. So I've gone ahead here and defined f. We recognize that this function f is a map from R2 to R2. No restriction on the domain. R2 is a nice open set. Now we can imagine we're just at any point in R2. Notice the domain here is for r and theta. So again, it's like imagine you just pick any radius and any angle. Without specifying more information about the anchor point, let's see what the Jacobian matrix would look like. The first row comes from taking the first coordinate function, that's r cosine theta, and differentiating first with respect to r, and then for the other entry with respect to theta. And then take the second coordinate function, differentiate it with respect to r, and then with respect to theta. Okay, so that's our 2 by 2 Jacobian matrix. When is this invertible? Well, let's compute its derivative. We have r cosine squared minus negative r sine squared, so plus r sine squared. So overall, that's r. So the inverse function theorem applies whenever r is non-zero. I'm going to sketch a picture here to talk a little bit more about this conversion between polar and rectangular coordinates, but hopefully this makes sense to you. If you just think about having a radius of 0, that places you right on the origin. And then it's like all possible angles, they don't matter at all, right? There's something degenerate about being right on the origin when you have a radius of 0. It's like you can't even specify what the angle is there. Okay, but let's imagine now that we are away from the origin. If I pick any positive radial coordinate and any angle, the inverse function theorem will apply to say that we are locally invertible. And we know that local invertibility is as good as we can get here. We cannot be globally invertible because cosine and sine are periodic functions. So we just know, based on the trigonometry here, that you cannot have a one-to-one relationship between x, y, and r theta pairings, because if you just go 2 pi further in your angle coordinate, you'll get sent back to the same place. But I would like to give you still a picture of, say, neighborhoods u and v on which we can imagine inverting this relationship between rectangular and polar coordinates. Okay, I just want to sketch some neighborhoods where we can say that our conversion between polar and rectangular coordinates is a bijection. Our function starts in R2 with r and theta, so those are the inputs, and we plug them into this conversion to go to the x and y world. So what I'm going to do is imagine some anchor point where r is non-zero. Let me just pick here. And I'm not going to say what theta is, so I don't know which quadrant I'm in, but let's say that I've landed in the second quadrant. Okay, so if I take this pairing of a radius and an angle and I plug it into my conversion, we get sent to this point in the second quadrant. Now what I would like to do is just design a neighborhood over here and see where it maps to over here. It's just a good exercise in really understanding polar coordinates anyway. So what happens if I say pick a radius which is slightly smaller, and I look at this straight line segment parallel to the theta axis back in our original domain? Where does that get sent to over here? Well, the radius is a little bit smaller than where I started, so we're going to move a little bit closer to the origin, and then we're going to go from, say, starting down here, an angle slightly less rotated through slightly more rotated. So that's like a circular arc. Let me just do solid lines. Okay, just imagine that this is kind of an edge of an open neighborhood. Same thing over here. If I pick a larger radius and go from a slightly less rotated angle to a slightly more rotated angle, that's going to send me like this, where the idea is that the angle is the same for the starting point here and here and here and here. Okay, and now if I connect along the same angle, go from the smaller radius to the larger radius, that's like filling in this line segment. And then similarly, if I go up to the larger angle now and connect from the smaller radius to the larger radius, that's over here. Okay. So that, let's use blue, this interior here gets sent to the interior of this kind of circular wedge piece. All right. Now, the thing is, if I took this rectangle and just increase it by 2 pi, we would get sent back around to the same wedge, right? So this axis here, this theta axis, it repeats itself every 2 pi revolutions because the cosine and sine functions are periodic. But if I throw away everything else and I just say that this is an open neighborhood U of my original anchor point where we know the conversion to be locally invertible because it satisfies the condition of the inverse function theorem, and this is V. If I restrict F as a function from U to V, then just as a map from U to V, it is invertible. So I could say, well, if I'm going to invert V, I'm pulling back specifically to this U. So from here to here, and ignoring everything else, the conversion is invertible. Now you might wonder, what are the best, or maybe I should say biggest, neighborhoods U and V on which we could invert the conversion between polar and rectangular coordinates? And that's not information that the inverse function theorem gives us directly, but we can basically take this idea of U and V and grow them into the most comprehensive domains possible just based on our knowledge of how this mathematics works. It might be easier actually to start with V. We realize that if I'm going to design some open neighborhood V, I can't have V do a full rotation. Like it can't include a full rotation around the origin because that would cause our conversion here not to be one-to-one, we would end up landing on the same point twice for different angles. So what we typically do is cut out of R2 over here a ray, including the origin. So you could just draw like a random ray and the origin, but typically we take out the negative x-axis. So let me kind of start backwards and define V first as all of R2, take away a closed set, which is the negative x-axis and the origin. So let me write that like that. Okay, so R2, take away the origin and this ray. That's an open set. How can I get to that in a way which isn't going to ever lose our ability to invert? And what we can do is say, all right, we need to basically fill in the first, second, third, and fourth quadrants, just not land on this. So angle-wise, I'm going to let my angle go down to negative pi, but not land on it through 0 around to pi. So let's do negative pi through pi. Just ignore this u for the moment. Okay, angles in this annulus here go from here to here, but if I don't include negative pi or pi, we will never land on the negative x-axis. And then your radius can be positive or negative, but if you allow for both, then you're going to overlap. So actually, let's just take this to be u. So u is like half of this strip here between negative pi and pi. I think I called it an annulus a second ago, but that was a mistake. I just meant strip. Okay. So if you let u be the Cartesian product of two open sets, 0 to infinity cross negative pi to pi, we don't have a full period for our function, so we're not going to land on the same Cartesian point twice, nor are we going to hit it with both a positive and negative radius with different angles. So this is going to cover all possible radii out from the origin and all angles except for those which land on this negative x-axis, and we're obviously not going to land on the origin because, as we know, that would be very problematic. Okay, so I can actually get a very large u and v on which our conversion to polar coordinates is bijective. And that's good because we want to use polar coordinates all the time. So we'd like to think that our ability to pass back and forth between these two worlds is fairly comprehensive. Let's wrap up with this exercise. So here we are looking at some world where we have four coordinates, u, v, x, and y. U and v are defined here. U is x cubed plus y cosine x. V is e to the x plus y. You can check that the point 0, 0, 0, 1 equals x, y, u, v makes both of these equations true. We want to know if near that point we can invert these relationships to say that instead of writing u and v as functions of x and y, we can write x and y as functions of u and v. Okay, there's something missing from this problem statement, and that is an explicit function. So what I would like for you to do first is pause and write down an actual f. So write down some function definition that we can then start to apply the inverse function theorem to. I wanted you to do this step first because, if you're going to apply the inverse function theorem, you want to at least recognize the function that you're trying to invert. I did the work for you on the last example where we looked at polar coordinates. So I said x and y equals f of r and theta, and then I described what f was. Here, we are saying that u and v can be thought of as functions of x and y. So that's the correct style function that we're looking for. And then we actually have what that function is. Its coordinate functions are x cubed plus y cosine x and e to the x plus y. Okay, and then that point 0, 0, 0, 1 is like saying 0, 1 equals f of 0, 0, which it does. Okay, so in the language of our theorem, 0, 0, this is like the point P. This is f of P over here. The question is, near P, can we invert this relationship, at least on some neighborhoods, where we can say that x and y can be solved for as f inverse of u and v? All right, now that we actually have the function f written down, we can do things like compute its Jacobian matrix. Let's just jump right into it. So in general, df is going to be a 2 by 2 matrix, and it's going to look like 3x squared minus y sine of x, and then differentiate with respect to y, we get cosine of x. Now differentiate this with respect to x and y. It's pretty boring. It's just e to the x plus y in both coordinates. Okay, that's the Jacobian matrix in general. But now let's actually plug in 0, 0. So I'm going to take this and evaluate it at 0, 0. And when we do, we get 0, 1, 1, 1. Okay, the question is this an invertible matrix? And the answer is yes. So it has two linearly independent columns. That's one way. That's the first thing I saw. If you do its determinant, you get 0 minus 1. That's not 0. That's what our actual theorem statement is. The determinant of this matrix is not 0, so it's invertible, which means the inverse function theorem applies. And in some ways, that's almost as far as we can take it. So it's like, yes, I can invert this function to say that near P f of P, so near the point 0, 0, 0, 1, x and y are functions of u and v. But I cannot do that explicitly. So I cannot tell you what the inverse function is. However, we can do things like write down the inverse function Jacobian at the point 0, 1. So going backwards, I can't say what f inverse is, but I can say what its Jacobian is. And we can also use that to do some approximations. This is our last exercise in this video. So once again, let's pause and take a moment to estimate x and y when u and v are very close to 0, 1. So namely when they are at the point 0.15 and 0.9. See if you can write down that first order approximation and use it. I took a moment here just to summarize the facts that we've collected so far. So we started with u and v as a function of x and y. And then by checking that this matrix was invertible, we were able to conclude that there were open sets u and v both in R2. U contains 0, 0, v contains the point 0, 1, so that f is a bijection from u to v. It's a bijection, so we can invert it. There exists some inverse function allowing us to think of x and y as functions of u and v. So we can invert the relationship we started with and say x and y are determined by u and v as we pass between these two neighborhoods. Here is that Jacobian matrix that we computed. I wanted to mention, if you haven't seen it in a while, that there's a very fast way to invert a 2 by 2 matrix. I can tell you, without knowing what F inverse is, that its Jacobian matrix at the point 0, 1 is going to be the inverse of this matrix. And for 2 by 2 matrix, it has a leading scalar out here, which is 1 over the determinant, so 0 minus 1, times what you do is you flip these entries. So 0, 1 becomes 1, 0. And then you negate these two entries, negative 1, negative 1. Okay, that does not look very nice, but let me write this one more time. So we'll have negative 1, 1, 1, 0. Okay, so 2 by 2 matrix inverse is very quick to compute if you have the original matrix. I should say a little bit more about what each of these entries are. So we have the matrix here. We don't have the function, but we know that it would be a function where the first coordinate output x is a function of u and v. That means that this row corresponds to the partial derivatives of x with respect to u and v. So this negative 1 up here in the top left corner, that's what we would think of as dx du at the point 0, 1. This entry up here in the top right corner is dx dv. And then down here, we have the partial derivatives of y with respect to u and v at the point 0, 1. So again, I can't work out what these coordinates are, so I don't know the inverse function, but I do know its partial derivatives. I just think that's really neat. And now let's use this matrix to approximate what x and y are when u and v are approximate or are 0.15 and 0.9. Just 4 coordinates here. I'm trying to keep them straight. That's like saying what is f inverse of 0.15, 0.9? It's approximately the linearized version of this function centered at the point we understand, which is 0, 1, but where we plug this into the linearization. So that's like f inverse at 0, 1 plus the Jacobian matrix at 0, 1, which we have right here, times the vector 0.15 minus 0. Sorry, I'm getting close to this. And 0.9 minus 1. So x minus the known x point, y minus the known y point. So 0.15 minus 0, 0.9 minus 1. Okay. And then we have all of these pieces of information. When I write equality here, that's referring to what's coming on this line is equal to this. It's all approximating the left-hand side here. F inverse of 0, 1, working in these neighborhoods where we are centered, is 0, 0. And then this matrix we just wrote down is negative 1, 1, 1, 0. And then times the vector 0.15 and negative 0.1. Okay. So let's see. Negative 0.15 minus 0.1 is negative 0.25. You can check me on this. And then 0.15. Okay, so when u and v are 0.15, 0.9, x and y are approximately negative 0.25, 0.15. That's all assuming that this computation is happening within these neighborhoods. So I'm making a guess here that u and v are large enough to include these values. How can you test if this approximation is good? Does it make sense? Take this. So this is approximately x, approximately y. Just to check yourself, make sure that I'm not way off base here. Plug this in for x, plug this in for y, back in the original function that we started with. So we have u and v defined as functions of x and y. Here's an x value, here's a y value. Plug these in for u and v and see if you get to approximately these values. It's going to be an approximation. But as long as you're reasonably close, then that means that probably I didn't make a mistake here. The closer these were to 0 and 1, we expect this to be better and better. And if you're way off, so if I've made an algebra mistake here, you'll get numbers that look very different. And that happens sometimes because algebra is hard. So it gives you, you can't actually know what this function is, so you can approximate it, and then you can feel good about your approximation by just kind of reverse engineering it. So what happens if I plug this xy back into what I started with? You should feel good if you get to something that looks like 0.15, 0.9. Okay, so that summarizes the inverse function theorem. It's a very important theorem. This example and the first example, again, were somewhat artificial because never do I really look at these expressions. But that change of variables exercise that we did is actually important, and we will return to that when we look at the change of variables formula in integration.